We've been talking about the shapes of orbitals that are involved in diels-alder reactions, the HOMO, the LUMO. And I want to come back to this issue of how do you make a diels-alder reaction fast? What's the difference between a slow diels-alder reaction that you have to heat and a diels-alder reaction that goes at room temperature or below? And if we want to understand that, we really need to go back to just regular ionic reactions in organic chemistry and ask ourselves in general what makes a reaction fast or slow. So I want to draw 4 different comparisons where some sort of a pi system adds into pi star. These are the most common types of reactions that you find in organic chemistry, like the aldol reaction. And I want to compare these possibilities so that we can ask, what is it that makes reactions fast or slow? So I'm going to start off with a very slow reaction. I don't think you ever spend your time worrying about whether alkenes will do nucleophilic additions to other simple alkenes. That reaction doesn't happen. You can store alkenes in a bottle and they don't dimerize in this sort of a fashion. That's a slow reaction. But if we soup up the acceptor pi star here, we can make this a little bit faster. This is still not a good reaction. You need to do something to soup that up in order to make that work at room temperature. If we make the alkene more nucleophilic by putting a resonance donor here, this will be a faster reaction. It's still not quite fast enough to go at room temperature if you don't give it some assistance. So maybe if you put a positive charge here on the acceptor by having an iminium ion, that's a more reactive electrophile. So you can just rationalize using things like resonance as to why these reactions get faster and faster as I change the substitution pattern. But I want you to be able to fall back on frontier molecular orbital theory and on MO diagrams when you rationalize this stuff. So let's go back to this very simple case here, and we'll draw an MO diagram, a molecular orbital interaction diagram, to represent this interaction of a filled orbital with an unfilled orbital. So let me go ahead and start off by drawing out a diagram here for this very simple case where I have this alkene that has very low nucleophilicity. So there's a pi orbital for a CC bond. It's got a pair of electrons in it. The most reactive pair of electrons in this molecule, isobutylene, looks like a pi orbital. So that's my HOMO. And it's adding to an empty orbital that's not very electrophilic. This isn't a carbonyl group, or there isn't some sort of a electron withdrawing group acceptor in resonance with that. So this is a very high energy LUMO. It's very hard to add electrons to this empty orbital here. And when these two orbitals interact, a filled orbital, this is the most reactive filled orbital, with this unfilled orbital, you don't get much out of that. So here's the 2 new orbitals that we get out. One would correspond to a bonding orbital, a new CC bond. The other new orbital that you would get out would be an empty orbital. It would correspond to an anti-bonding orbital between these 2 carbons. And we call this drop in energy, which would be very small, we call that the interaction energy. This is, to a large extent, what the molecule would have to gain by interacting in this way, that little energy there. So I'm not sure if I have enough room here. I'll write interaction energy. Interaction. So very small. So what's the effect of of changing this double bond here into a carbonyl group or an iminium ion? As we replace carbon with a more electronegative atom, or one that has a positive charge, what we expect is that this LUMO is going to drop in energy. It's going to be easier to add electrons into that. So let me sketch a new diagram over here for what looks like a better reaction, a new MO energy interaction diagram. And I'll watch what happens as I drop the energy of this orbital here for this acceptor orbital so that it looks lower. It's lower in energy. It's easier to add electrons to that. Likewise, if I put a resonance donor on here like a methoxy group that has a lone pair, it's going to raise the energy of the HOMO. It's going to make this more nucleophilic. And so let me represent that by making this filled orbital higher in energy and more nucleophilic. So I've done 2 things here as I've walked across this sort of reactivity series. I've raised the energy of the HOMO and I've lowered the energy of the LUMO. And because these are closer together, I'm going to get more interaction energy out. I'm going to get a new CC bond that's way lower in energy than this filled orbital that I started with. And I'm going to get a new antibonding orbital for this new CC bond that's way higher in energy, but I don't pay any penalty for that because there's no electrons in there. So it doesn't matter that I really raise the energy of that antibonding orbital that I get out because it's empty. So you really benefit. So what we're really looking for here, what we're really looking for in terms of what makes reactions fast, and I'll try to summarize that here in the middle. So one property of fast reactions is that more nucleophilic our code word for more nucleophilic is that things have a high HOMO. You raise the energy of the HOMO, those electrons are more nucleophilic, more reactive. For the electrophile, more electrophilic corresponds to a low energy LUMO. It's easier to add electrons to an empty orbital that's lower in energy. That just kind of makes sense. And overall, a fast reaction has a small gap between these two. Because if you push up the energy of the HOMO and you lower the energy of the LUMO, you end up with a smaller HOMO-LUMO gap. So we often use this term HOMO-LUMO gap as a code word for saying fast reaction. Small HOMO-LUMO gaps correspond to fast reactions. So I think that's easy to see here. So fast but really, you don't need to use that kind of fancy language. You could just say more nucleophilic and more electrophilic. Okay, exactly the same thinking applies to diels-alder reactions. If we want to make diels-alder reactions fast, then we need to think about combinations of reagents that have small HOMO-LUMO gaps. And so let's compare that. So fast diels-alder reactions will resemble good nucleophiles plus good electrophiles. That's what we should expect. Let's take an example of a slow diels-alder reaction. If I just take a simple diene and a simple alkene, we call that the dienophile. This is not a fast diels-alder reaction. The canonical classical diels-alder reaction, where this acts kind of nucleophilically. We think of the dienophile as being the acceptor, but you could reverse the roles and it still works in terms of thinking. That's not really a fast reaction. Let's contrast that with a diels-alder reaction that I would expect to be fast. I would expect this to be a fast diels-alder reaction. And let's talk about why we expect that to be fast. Oftentimes you can rationalize all of this stuff here with respect to reaction speed just by drawing some resonance structures. So if I draw a resonance structure to help me understand the effect of this methoxy substituent, I'm going to use those lone pairs and make them donate into this alkene. And so another way of describing that is by drawing out the resonance structure where I can see that it ought to be very nucleophilic on this end carbon. That this diene ought to be very nucleophilic on the end carbon. It's a good nucleophile. And likewise, I can draw a resonance structure for this acrylonitrile that makes it kind of obvious that it's very electrophilic here on the end carbon as well. I've got something that's very nucleophilic, very electrophilic. This ought to be a fast reaction. Now it's true, it is true in this reaction that you can also think of the alkene as being the nucleophile and attacking the diene. But we only need one of these combinations to be fast. We only need this to be a good nucleophile or this alkene to be a good nucleophile. Only one of them has to be a good nucleophile in order for us to explain this fast diels-alder reaction. So let me sketch out the slow case, the molecular orbitals that are involved in the slow case of a diels-alder reaction to help us understand that. So let me go ahead and draw out the frontier orbitals for a diene and an alkene. So I'll start off with the diene. You remember that resonance kind of pinches the energy of the HOMO and the LUMO. when you have resonance. Resonance effects tend to, so if I were to sketch out the energy of just a plain carbon p orbital, it would be right there. That's just the energy of a simple carbon p orbital. And so the HOMO for a diene is going to be up here. Sorry, the LUMO for the diene is going to be up here, and the HOMO is going to be down here. That's the filled orbital. Now a simple alkene that has no resonance, that has a much higher energy LUMO and a much lower energy HOMO. So a simple alkene is not as nucleophilic. A simple alkene, it's not as easy to add electrons to that, so that should make sense. So the effect of resonance is to kind of pinch down these orbitals. Now, what I'm really interested in, if I draw a picture where this alkene, the diene, attacks the dienophile, this is the nucleophile, this is the electrophile, that's what my first arrow is saying, then I want to think about this pair of electrons in the diene. Let me just draw well, this is the diene here. And this is the dienophile. What I'm really drawing with that arrow is the interaction between this filled orbital and that unfilled orbital. And if I measure the energy of that gap here, the HOMO-LUMO gap, I would draw a line that looks like that. And if I think about the interaction of this dienophile with the diene, where this attacks, now this is the nucleophile. Now the alkene, the simple ethylene, is the nucleophile, and this is the electrophile. So that means I'm talking about this HOMO-LUMO gap. And those will be identical. For this very simple case, the HOMO-LUMO gap, where this acts as the nucleophile, and the HOMO-LUMO gap where this acts as the nucleophile, will have the same relative energy. Neither of those is better than the other. They will both contribute to bonding in the reaction. But there's nothing to really make this a fast reaction yet. So let's draw the case where I have substituents on there. And let's draw an MO diagram to help us think about why this is fast. And there's an asymmetry here. So I'm going to draw a little dashed line here. Let me try to draw this sort of midway. And this will be the energy of just a simple carbon p orbital on carbon. Okay, now remember what's going to happen is I add a donor here onto my diene. I'm going to raise the energy. I'm going to raise the energy of the HOMO. I'm going to raise the energy of this system. And so I'm going to raise the energy of this HOMO now to where it's, I'm going to try to make sure it looks higher than it did before. And there's my pair of electrons. So now my diene has this high energy HOMO because of that lone pair on the oxygen donating into that, making it more nucleophilic. This is now more nucleophilic. And at the same time, because I have a resonance withdrawing acceptor here on this alkene, that's going to lower the energy. It's going to lower the energy of the LUMO for this system. So here's my, I don't know how to do this without, I want to draw some label lines. There's my two components there. And so what you can see is that you don't win equally. There's one particular HOMO-LUMO gap that is small here, and that's this one. In other words, by making this a better nucleophile and that a better acceptor, what I've done is I've shrunken the HOMO-LUMO gap. The other one gets worse, but that's okay. The overall reaction is still faster. It is still concerted, and it is still a faster reaction than the parent system. And this is generally what you see in diels-alder reactions. You have some substitution pattern that makes one a better donor and the other a better acceptor, and that creates one single HOMO-LUMO gap that is small in energy. And that's all you need for a fast reaction, is that one HOMO-LUMO gap tends to dominate. So when you look for fast cyclo-addition reactions, you want to be looking for something that's nucleophilic and something that's electrophilic, just like you've seen before.
So it looks like both the bonding and anti-bonding of the diene are going up, but then the dienophile going together.
I'm trying to draw, this is a resonance
Right.
acceptor, and resonance pinches. So I'm kind of trying to graphically draw that this is pinched a little bit and lower in energy. And there's only so much I can do. But you can back that up by doing calculations. You could get actual quantitative numbers for this by jumping on the computer and calculating the energies, and you could plot those out yourself. So yeah, I am trying to pinch that. Okay, so all that stuff you could rationalize just by drawing resonance structures, but when you need to, you can draw out MO diagrams that back up what you're saying. Okay, I want to compare some actual reactants in diels-alder reactions. There's a lot more going on than just the energies of the orbitals. There's things like strain, sterics. And so I want to draw a series of substrates and reactions so we can get a sense for quantitatively how do those things affect reaction rates. And I'm going to start off with this very simple diels-alder reaction. It's very common to run this in undergraduate chemistry laboratories. You take maleic anhydride. This is a great dienophile. Look, it's got 2 carbonyl groups on it. That's going to be a great dienophile. Okay, so when you take, I'm going to assign some relative rates for diels-alder reactions. Let me just draw a dotted line here. I'm not going to draw the arrow pushing, so you can see the connectivity. I'm going to assign this a relative rate of 1, and we'll compare everything to this relative diels-alder reaction rate. If I take a very similar looking diene, and all I do is I just glue a cyclohexane ring onto one side, I increase the speed of this reaction by 100-fold. 110 times faster. And to a large extent, this has a lot to do with the fact that I've simply forced these 2 dienes into an S-cis geometry. The problem with just plain butadiene is it spends a lot of time, most of its time in fact, in this transoid geometry, S-sigmoid trans. It spends a minor amount of its time in this geometry that's needed for the diels-alder reaction. And so that's a huge advantage for this diene. It spends 100% of its time in this S-cis geometry that you need. I'm going to draw this for comparison. Actually, having a fuller discussion of this would require us to spend more time on aromaticity. This actually, all 3 of these rings don't have the same aromaticity as a simple benzene ring. You get the maximum amount of aromatic resonance energy by having just a simple benzene rings. This second and this third ring don't enjoy the same 35 kcals per mole of aromatic resonance energy. And when you do a diels-alder reaction across this middle bond here, not on here, but on here, you get 2 isolated benzene rings with the maximum amount of aromatic resonance energy. And that turns out to be a very efficient, a surprisingly efficient diels-alder reaction, even though it looks like it's disrupting aromaticity. I'm showing you this because I'll show you some more examples using this diene here, because it's easy to monitor by UV vis spectroscopy, the rates of diels-alder reactions. Cyclopentadiene is by far the most common diene used in diels-alder reactions. If you look, what's the preferred angle for an sp2 hybridized carbon? If I just take a simple sp2 hybridized system that looks like this, what's the preferred angle, bond angle there? 120 for sp2. This isn't 120, it's like 108 degrees. 4 times over, this thing has to pay this angle strain price for being in a 5-membered ring. So when you do a diels-alder reaction here, these 2 carbons get to relieve some of that strain. They want to be 120. It'd be a lot better if they were sp3 hybridized. So cyclopentadiene has this angle strain relief that it gets by doing diels-alder reactions. So when you look at the rates for cyclopentadiene with maleic anhydride, it's about 1,000 times faster than just the simple canonical diene. And so to a large extent that has to do with that angle strain. Okay, let me take a few more examples using the maleic anhydride system. And again, this has a relative rate of 1. If I put that methoxy donor substituent on there, right, we can draw MO diagrams, but that doesn't actually, those MO diagrams that we sketch out on a piece of paper don't tell us about the actual speed. That's 10 times faster by having a methoxy donor on there. You get a slightly better effect. Really, if you draw resonance structures, your prediction would be that this lone pair on oxygen only affects the bottom double bond. It doesn't actually affect the top. There's no resonance structure you can draw where this lone pair interacts with that top double bond. So you'll find that it's better to have the methoxy group on the top diene with a lone pair. Now you can draw resonance structures that interact with all the double bonds in that system. And this is a better Not substantially, but it's a better diene for diels-alder reactions. By far, the most common pattern of substituents for diels-alder reactions would be to have 2 oxygen atoms. This is called Danishevsky's diene. So if you're taking synthesis, you know you can make silylenol ethers from ketones. That's very easy to make in one step. And now it's doubly activated. I don't have exact numbers for this. It's greater than 100-fold faster than just the parent diene. It's very fast. And it leads to a substitution pattern that's very powerful. Okay, let me go ahead and continue drawing some reactions. And these are numbers that were measured using this anthracene derivative, dimethylanthracene. Again, very easy to monitor those reactions with UV-vis spectroscopy. So if I look at the reaction rates for this diene with this dienophile, this is methyl acrylate. This is 700 times faster. So how do I draw these? I'm going to use kind of sorry for the curved lines. I'm just trying to show you the connectivity there. So when you do diels-alder reactions with this dimethylanthracene and this methyl acrylate, 718 times faster than just this simple system. Okay, now let's compare that with an alkyne that has 2 activating groups. This is called dimethylacetylene dicarboxylate. It's often abbreviated as DMAD. So if on my problem sets I say DMAD, I'm talking about an alkyne with 2 carbonyl group resonance acceptors that can really lower the energy there. And so now this is I'm sorry, I'm running out of room here, 1,400 times faster. Boy, if you want to do a fast diels-alder reaction, that's a great dienophile to use. Right? What if you could do all of your chemistry 1,000 times faster? You'd be done with your Ph.D. in, I don't know, hours. You'd be counting hours instead of years. It's actually comparable to have a nitrile on just a simple alkene as to have 2 esters on the alkyne. Alkenes are intrinsically better in this case. And finally, if I put 2 acceptors on an alkene, (2,000 times faster than just the simple canonical case that I had over here. Actually, we should be comparing it to this case over here. Maybe I would say 10 times faster than that simple case over there of maleic anhydride plus anthracene. Okay, so you can get a sense for this range of reactivities. You can get thousands of times faster just by changing the substituents. That'll make the difference between reactions you have to heat and reactions that will go at room temperature or maybe even below. Okay, so let's talk about regiochemistry and diels-alder reactions. There's a very simple rule that allows you to predict regiochemistry in diels-alder reactions. And I love simple rules. And our simple rule is called the ortho-para rule. I'm going to chest out another pen here because I think this one is dying. And here's the way we think about the ortho-para rule. In the typical case where you have fast diels-alder reactions, you have a donor group on the diene. Your diene is usually the nucleophile. And you have an acceptor group on your dienophile. And when you do this, there's 2 different orientations in which this could undergo diels-alder reactions. One orientation for the products would be to have these groups oriented 1,4, and if you kind of imagine that to be a benzene, it's not a benzene ring, but if you imagine that to be a benzene ring, it looks kind of like it's got an ortho relationship. The alternative orientation would be to have the nitrile pointing down if I reorient this nitrile and flip it upside down, I could get that meta-type relationship. So again, this isn't a benzene ring, so I'll just put in parentheses, this looks kind of ortho. And this looks kind of like it's got a meta relationship. And the ortho is preferred. And if you drew resonance structures, you would see that this end is more nucleophilic than that end on the top. And this end on the bottom is more electrophilic. And it's just resonance structures you could rationalize this. If you had never heard of this ortho-para rule. So there's another, we can also add the methoxy group to one of these internal carbons over here. I'll draw it on the bottom one. And when we draw out the products for a diels-alder reaction, now the choices are something that looks kind of para. It's not a benzene ring, but if it was, you would refer to that relationship as para. And the other alternative for our substitution pattern would be to have these two groups with that quote-unquote meta-type relationship. And you don't see the meta. What you see is the para relationship. So these are the two favored types of substitution patterns. You get regio control in the diels-alder reaction that's predictable. And it's predictable based, once again, based on resonance structures. If you'd like to rationalize this, draw a resonance structural. You'll see this is the nucleophilic carbon, that's the electrophilic carbon. And so there's this sort of matching here. And this is the nucleophilic carbon, and that's the electrophilic carbon. And so you'll get that very powerful matching. And you could have predicted that. Okay, so let's go ahead and look at stereoselectivity in the diels-alder reaction. And we're going to look at something called the endo rule. In most cases, your dienophile has a resonance electron withdrawing group. That's when you get fast diels-alder reactions. So when you have a resonance electron withdrawing group on the dienophile, like a carbonyl or a nitrile, you'll find that in the transition state, it prefers to orient underneath the diene, even though that's more sterically hindered. So if we draw out a reaction between cyclo-pentadiene, here's the implications of that, and methyl acrylate, and we do a cycloaddition reaction, you get two different products, two different stereoisomers out of this. So I'm going to draw a Norbornyl ring system. I'm going to start by drawing something that looks like half a chair. You can just draw a chair and erase one side. And I'm going to draw two perfectly axial bonds here. And here's the bond that's closer to us. So this is the ring system you get. You get a Norbornyl ring system out of this diels-alder reaction. And there's two different stereoisomers that you get out of this. In one of the stereoisomers, the ester group is oriented underneath the Norbornyl ring. And in the other stereoisomer, the ester is in the less sterically hindered position. The terms we have for these are endo and exo. So we refer to this as endo, where this carboxymethyl is closer to the 2-carbon bridge as opposed to the exo orientation, where the carboxymethyl is closer to that 1-carbon methylene bridge. And the endo is favored. Surprisingly, it's more hindered. The product is less stable. It's favored. The endo product is favored. Substituents prefer to be exo on orbital ring systems. And yet, this is the one that forms faster. It forms 4 times faster. That means the transition state leading to the endo product is lower in energy by 0.8 kcals per mole. Here's the rationale for that. And I'm going to do my best to draw some sort of a diene, kind of in this 3-dimensional, I'll try to make this look really 3-dimensional here. So we're kind of looking at the diene, kind of, and I'm not going to draw the whole cyclopentadiene. I'm just going to draw the 4 carbons, where these 2 carbons are closer. And let me sketch out the orbitals for the HOMO of the diene. This is kind of like the nucleophile, and this is kind of like the electrophile. So if this is kind of like the nucleophile, I'm going to draw the MOs for the HOMO of the diene. And the HOMO for a diene is big, and the LUMO is big on the ends. So first I'm going to put the relative sizes there, and then I'll fill in the phasing. And I'm going to hash the top on one end, and on the other end I'm going to hash the bottom. So that's my picture for any kind of a diene, not just cyclopentadiene. And now, importantly, I'm also going to phase this the other two p-like orbitals that contribute to making the HOMO for the diene. Okay, so that's the HOMO for the diene. Now, underneath, I'm going to draw in the preferred transition state. I'm going to draw. I'm not going to draw the whole ester part. I'm just going to draw the carbonyl. I'm going to draw my dienophile interacting with that underneath. And let me try to draw the orbitals for that. And maybe I'll do it in green, so I have this, so I can distinguish the colors here. And let me just kind of fix my drawing here a little bit better. So this is kind of like the electrophile, the enone, so I want to draw the LUMO for that. And the LUMO is big on the end carbon, not quite as big on the alpha carbon. But because this is like a diene, I also have some other orbitals here to draw for the carbonyl. And because this is kind of like a diene, it's 2 pi systems connected. I have to phase it like I phase a diene. I'm going to draw the LUMO now. I'm going to draw this one. I'm not doing a good job of avoiding these 2 here. Let me make sure I get the phasing right. So now for the LUMO of the diene, I'll write LUMO down here. Now the phasing is the same on the ends instead of opposite. So for a LUMO of a diene, the phasing is the same on the ends. For the HOMO of a diene, the phasing is opposite. You flip. Now when I look at the interaction of these orbitals here, as I form a bond between this carbon and this carbon, there's going to be a good bonding interaction between these 2 hashed regions. That's why you form a bond in a diels-alder reaction. And then between these carbons here, I've got the correct phasing to form a bond. And if I flip the carbonyl underneath the diene, there is an additional interaction here. The phasing is correct. You can't not have interaction there, right? If the phasing is correct, there will be interaction between these orbitals. What this picture tells you is that the most reactive pair of electrons in this system spends its time in all the places where I've drawn orbitals. The most reactive pair of electrons in this HOMO is spending time a little bit above this carbon atom. And there's an empty orbital here, and there will be some interaction. It's not as strong as the primary interaction. You don't get a full-on bond, but that's where you're getting, some of that 0.8 kcals per mole. You're actually getting more because there's a steric penalty. So this is worth something in lowering the energy of the transition state that leads to the endo product. We call this secondary orbital overlap, this interaction here. And this is the accepted explanation for why you prefer the endo product, even though it's more sterically hindered. And this is true for acyclic dienes as well. This is not some cyclo-pentadiene thing. The electron withdrawing groups that you almost always have on your dienophiles will tend to want to wrap underneath the alkene. Now, you could bulk up the sterics to override that 0.8 kcal per mole preference. I mean, it's possible. You often see that preference undone by sterics or when you do intramolecular diels-alders. But that's the intrinsic preference, is to have secondary orbital overlap. Okay, 4-to-1 doesn't sound very good as far as selectivity goes. And when you do thermal reactions, you prefer para and ortho products. You don't get perfect selectivity. Usually when you do diels-alder reactions in organic synthesis, in modern organic synthesis, you're using catalysts to speed them up. So let's talk about the effects of Lewis acids. And there's two pronounced effects. So first of all, they accelerate the diels-alder reaction. We'll talk about that. Up to 1,000,000 times faster by throwing in a Lewis acid. But the other benefit of adding Lewis acids is that they improve the regioselectivity and stereoselectivity. All of the arguments that I'm making right here about secondary orbital overlap or that ortho-para rule and how you can use resonance structures, all of those arguments will be more powerful if I coordinate a Lewis acid to the enone, which will magnify the differences in the shape of the frontier orbitals. So let's go ahead and draw out some reactions so we can compare the effects of catalyzed and uncatalyzed. So I'm going to start off with this very simple pair of diene and dienophile. And I don't have a powerful donor group, just a methyl group. Right now it's just CH bonds there that are the donor, not oxygen lone pairs. That's pretty lame, CH bonds. So when you do a diels-alder reaction, you get two different products out of this, regiochemically. You get one that looks kind of pair on one. And again, this is not like a resonance donor. CH bonds are not very powerful resonance donors. So if you just simply heat this up to make the reaction work, 120 degrees, you get about a 60-40 ratio of these two products. The para is favored, but not by a lot. And again, that's because methyl is not a super powerful donor. But if we simply throw in a Lewis acid, now the reaction goes at lower temperature. Now you don't have to heat the reaction. You just throw in stannic tetrachloride. And that coordinates, of course, here to the carbonyl. Any arguments you were making about why you want to attack here with nucleophiles are now more powerful arguments. So it makes it more electrophilic here. It distorts the lumo, so it's bigger here on that carbonyl. And so now, not only do you get a reaction that goes at lower temperature, you now get higher regioselectivity, 96-4. That's the effect of Lewis acids. So if you're in the lab, yeah, you could just heat things up. But usually people add Lewis acids to diels-alder reactions. Let's take another example where we can compare not regiochemistry, but stereochemistry. I should have kept that drawing on the board. So if I take that example that I just erased, which was cyclopentadiene plus methyl acrylate, and I compare the thermal reaction versus and I'm just going to write the words endo and exo here, since you just finished drawing those structures. So if I look at the thermal reaction, I get an 82 to 18 mixture, 4-to-1, like I said, favoring the endo product. But if I throw in a Lewis acid that can coordinate to the carbonyl, aluminum trichloride, the endo selectivity goes to 99 to 1. And again, the endo product is sterically more encumbered. It's sterically less favorable. And yet you get this huge influence that it forms at least 100 times faster. I don't know how accurate the 99 to 1 is, but it's 100 times faster to form the endo product when you throw in the aluminum catalyst. They're both faster. You form both of the products faster, but the endo product starts to form way faster. Okay, so this is typical of diels-alder reactions. In most diels-alder reactions, in 90% of cases, the diene acts as the nucleophile and the dienophile acts as the electrophile. That's the common arrangement. Now let's talk about the less common arrangement. Because in theory, either one of those components can serve as the nucleophile. I hate this word, this phrase for this, because it sounds really clumsy. But when we reverse the roles of the components, let me just draw out a regular diels-alder reaction to remind you. Generally, we think of the diene as the nucleophile. But you're forming two bonds in the diels-alder reaction. This dienophile is also serving as a nucleophile. So there's two different ways you can speed up the reaction. You can make the diene a better nucleophile, or we can make the dienophile a better nucleophile. And that's the less common case, and we call that inverse electron demand. So this is generally a slow, diels-alder reactions are generally slow. But we can speed this up by making the alkene the more nucleophilic component of the reaction. And I'm going to draw one pair of reactants in the middle, and I'll have two different things that I'll draw on the side here. So first of all, let me redraw my dienophile component, and just arbitrarily I'm going to make it a ring. The important point is there's an oxygen now on the dienophile. Now instead of having a carbonyl group on my dienophile, I'm putting a resonance donor, that lone pair there. So now the dienophile is the better nucleophile. And if I really want to make this a fast diels-alder reaction, if this is going to be the nucleophile, I need to have a good acceptor. And here's my acceptor. It's kind of like an enone, but it's even better than an enone, because by replacing carbon with nitrogen, I lower the energy of the lumo even more. So yeah, in theory, I could have two carbon atoms there, but I'm just really souping it up. This is a common reagent, diethylacetylene dicarboxylate. So now here's the nucleophile, and here's the electrophile. Everything's reversed. And this is the other way to make diels-alder reactions faster. Instead of making this the more nucleophilic component, we can reverse it. And now this is the inverse of normal. Let me just draw out the resonance structures here for these two components so we can see why the regio. If I take this lone pair and I donate it over here, I'm going to see that I expect, just based on resonance structures, that dihydropyran, this enol ether, is going to be nucleophilic on this top carbon. That's the nucleophilic part of this enol ether. And if I redraw a resonance structure for this diazo compound, I would tend to push the electrons to the carbonyl, and I would expect this nitrogen to be the best acceptor. So let me draw that resonance structure. Sorry, I don't want to add extra arrow pushing there, so I'm trying to, sorry, I'm not drawing the arrow pushing for the resonance structures. I just don't want to overly increase the complexity here. And so here's the key resonance structure for that acceptor, the electrophilic site in the lumo. I expect this to be a very strong, most reactive here on nitrogen as an acceptor. You wouldn't expect nucleophiles to attack the carbonyl oxygen. That wouldn't make any sense to you. That's the most electronegative atom in the system. So you kind of expect this to pair up with this regiochemistry. This is the regiochemistry you expect when you look at the HOMO and the LUMO for these molecules. Okay, so again, let me just draw I'm not going to have room over here, so let me come over here and draw the MO diagram for this inverse electron demand, just so we can rationalize what's happening. And I'm going to start by drawing the regular diels-alder reaction and the HOMO and the LUMO. So for a regular diels-alder reaction, I've got the diene. So remember, dienes have this sort of pinched in, that's the effect of resonance. The HOMO is higher, the LUMO is lower. It's easier to attack a diene. Dienes are better at attacking other things. That's what this picture is telling us. And I compare that to a simple alkene, and I've got this higher energy HOMO and LUMO. And again, there's nothing really special about this. I look at the HOMO-LUMO gaps. They look, nothing really that great. They both have about the same, they have the same gap energy. So now I compare that here. I'll have the same HOMO-LUMO gap regardless of which one I treat as the nucleophile or the electrophile. But when I do this inverse electron demand thing, and again, here's my midline. That's just the way I imagine a carbon p orbital. And if I imagine this to be a carbon p orbital, it helps me to understand what happens if I replace that with a more electronegative atom. So now when I take this system that has not just a diene, but I'm replacing one carbon with an oxygen atom, I'm replacing two other carbon atoms with nitrogen atoms, and all these electronegative atoms, by replacing carbon with a more electronegative atom, I'm going to drop the energies of all these orbitals. They're all going to drop because I'm replacing carbon with more electronegative atoms. And how do I really emphasize this drop here? There we go. It kind of looks the same. That's pathetic. I want this to look lower now. I'll drop that below the midline. Okay, so now what I'm really doing is I'm lowering the energy of the LUMO here, making this a very powerful acceptor. This is why you see this used with phosphines. It's a very, very powerful and reactive electrophile. Now, by having an alkoxy group, an oxygen with lone pairs on there, on the dienophile, that makes it a better nucleophile. I'm going to raise the energy of those systems. And so I end up with this HOMO-LUMO gap. It's very small, and that's what drives this reaction, is that small HOMO-LUMO gap. So you can reverse the roles of these reactants in a diels-alder reaction. And that's called the inverse electron demand diels-alder reaction. Let me give you an example that's more interesting than this. Actually, this is an interesting example, but I'll give you one that's more interesting. It's very easy to do aldol or Novanagle type condensations with these types of enones. And there's a very classical terpene called neral or dihydroneral that you can use. It will very easily allow you to assemble this by condensing with an aldehyde. And so when you do that Novanagle condensation with an aldehyde to produce that enone, under the conditions of the reaction, it will automatically undergo an inverse electron demand diels-alder reaction. This is an inverse diels-alder reaction, right? The diene is the electrophile. Usually the diene is the nucleophile. And so this undergoes spontaneous, at least under the conditions of the reaction. I'm drawing this out because maybe obviously to you. This is THC, or delta-9 tetrahydrocannabinol, which is the active ingredient in marijuana. And you can make it almost completely in one step. You still have to add this extra double bond here, but it's very easy to aromatize this ring with oxidants. And this synthesis takes advantage of the facility of this intramolecular inverse electron demand diels-alder reaction. Okay, I've got one last thing to talk about, and that is stereospecificity. And this is important because stereospecificity is a classical criterion for pericyclic reactions. And I want to help you understand stereospecificity by contrasting it with stereoselectivity. What is a stereoselective reaction? It means you prefer one stereoisomer. For example, you prefer endo products over exo products. You prefer cis products over trans products. You prefer anti products in relationships over syn. You prefer R stereochemistry versus S stereochemistry. Those would be examples of stereoselective processes. Let me give you an example of a stereoselective reaction. Just an intramolecular conjugate addition reaction. So I've got this sort of Michael acceptor there. Not great because there's not a lot of partial positive charge here, but because it's intramolecular, this works. Right? Oxygen's very it's got a lot of negative charge. But this reaction works. If you had catalytic base, you can get this alkoxide to undergo an intramolecular Michael reaction. And the preferred product in this process is to give the product in which these have a cis relationship. And if you draw a chair, you'll understand that that's good because these both get to be equatorial when they're cis. And what's important here is it doesn't matter what the geometry of this double bond is. You can start with E or Z and you will always get this cis product. This is an example of a stereoselective reaction. It prefers the cis isomer, and it doesn't matter what the stereochemistry of the starting material is. Now I want to contrast this process up above that's stereoselective with one that's stereospecific. Diels-alder reactions are stereospecific. And they're stereospecific because the stereochemistry of the starting materials determines the stereochemistry of the products. So if I start with this dienophile, this is called dimethyl fumarate, and I do a Diels-alder reaction, the product that you get out of this reaction has an anti-geometry between the two ester groups. You start with these two groups anti to each other, you end up with those two groups anti to each other, and you retain that relationship because the transition state is concerted. There's no opportunity for bond rotation since it's a single step reaction with a single transition state. But there's no way by running just one reaction that you could determine that this reaction is stereospecific. The only way that you can make the statement that this is stereospecific is by testing both of these different stereoisomers of the dienophile. In other words, until you show that the other isomer of fumarate called malleate, dimethyl malleate, gives you the cis relationship, until you do both of those reactions, there's no way for you to say that this is stereospecific. But after you show this relationship, now you can say this is a stereospecific transformation. It's stereospecific. One isomer, the cis isomer gives you cis, the trans isomer gives you trans, the cis isomer gives you cis, that's stereospecific. Different from stereoselective. Okay, so during discussion section, we'll try to work some problems on Diels-alder. Maybe have a few practice problems that'll help us get ready. There's an exam on Friday, and I have office hours tomorrow at 12 if you want to come see me then. So I'll see you guys at noon when we can do some practice problems.